saw somebody coming in and leaving the room, and I'm sure I'm looking at it, I think it was Yinhao, right? So maybe we should harass him. We should make him all right. While we're waiting for him, so we have, I believe, 10 lectures left, approximately. Okay. Actually, precisely, I believe 10 lectures, and obviously, you know, some think that we're covering too much. Some may think we're not covering anything substantive. Not yet, right? Because the subject is huge, right? So are we done with sampling methods? The answer is absolutely not, okay? So I started, I think, yesterday looking on, working on topic A, then I said, no, maybe not, topic B, topic C. So I decided to switch to sequential Monte Carlo maybe for 2 lectures, because I know at least 2 of you in the class are interested on the topic. So there is a lot of other things in between that I will not have time to cover, but maybe, who knows, maybe we'll come back in November, in early November. So this topic itself, it requires literally about 5 hours of lectures to cover it. Okay, and I have approximately, I think, 6 or 7 sort of lectures, each of them 100 pages basically on the topic, because it's a huge topic. So what we're going to try to do is maybe today have a very elementary introduction, okay, for those who have not seen the stuff before, and maybe one more lecture on some details, but that's it. Okay? And I think potentially I'm going to give you a homework set because this is a very, very important topic. All right, so you can extrapolate from the title. We're going to expand on the concepts of importance sampling for nonlinear, non-Gaussian dynamic models. But I have to tell you, in case you don't really care about dynamic models, sequential Monte Carlo methods are very powerful. They can be applied to problems with zero dynamics. You just need to make your problem to look actually like dynamic, where the time can be some imaginary variable. And there are many methods who do this for static problems. So, you know, I may give you homework again that works in the direction. But if dynamics is not of your interest, I am just telling you that most of the modern applications I see of the methods have nothing to do with dynamics. But dynamics is an easy way to understand what's going on. Obviously, this is a research topic. And that's why you see lots of references. I had to actually work yesterday on every single of them to fix the links. So I would love to hear that at least somebody hit one of those links, so it was not such a waste of time. Okay? So please, just out of curiosity, hit of this. And you can see, for example, you know, I look here, the video lectures of Professor Doucet, and my notes literally follow a lot of the courses that he has on the subject area, but he has a lot of video lectures. So if you really want to learn a lot about the subject, you can follow his videos. And most probably he gives this sort of course annually, so you can find more updated links. All right. Lots of references. Okay, so when is sequential Monte Carlo going to be useful? The answer is when we have to approximate a sequence of probability distributions. So sequence, today in what we will refer to, we will look sequence in time, but it can be again on imaginary time, and actually for those in physics, or those who are interested in courses of simulated annealing, can be sequence in temperature. All right, so, or can be a sequence that you artificially generate that will take you from the prior to the posterior. And we may do this actually on Wednesday as a passing example. So the obvious application is dynamics and what is called this very general form of dynamical systems that goes under the name of hidden Markov models. So I'm going to have today to spend 70-80% of the time on some basic things on hidden Markov models. That topic by itself is really 2 or 3 lectures, so we will compress it to half a lecture today. Don't know if that's possible, but we're going to try. Okay? We just don't have the luxury of covering this topic. By the way, for those who are going to take the probabilistic graphical models next semester, we're going to be able to come up sort of with a graph theoretic interpretation of these models that allows you to write the questions down without remembering anything. So visually, you'll be able to work with these models in a much better form than we will do today. So beyond dynamics, I can tell you, you can use this to calculate eigenvalues, free energies, and free energies basically lead you to anything, solve differential integral equations, simulate with molecular simulations, polymer chains. You just mentioned to me, and actually any problem you may have in mind, anything, I will put it on a sequential Monte Carlo setup, so you can practically do everything. An alternative method name that goes under sequential Monte Carlo is particle methods, right? And of course, most of the Monte Carlo methods we have seen up to now, they are really particle methods because the sample distribution is represented with particles, but here we will make these particles to be sort of dynamic, and we will allow them to evolve with time. Okay, so first I have to tell you a little bit about this state space models. Again, I am assuming the significant part of the class has not seen this, certainly not with a statistical context. So this is what we have. We have a Markov process, xn for n 1 to infinity. We start with some initial state, and I think even our random walk examples was a Markov process. So we start with some initial state, and we have a transition model that is defined by this probability f. I want you to remember the names, so when we see this in the slides, we don't get confused. This will appear once in a while as the probability of your initial state. This is the transition probability. And again, it's a Markov model because you notice the xn is selected given xn minus 1. That's the only information you need. Okay? So if you take the whole chain and you want to write the joint probability distribution, and by the way, I'm going to call this prior distribution because at this point I have no data. Okay? You will see why it is called this prior, because I'm going to shortly enhance this model. But this prior distribution is basically the probability of being at x1, and then the product of this transition probability is from xk minus 1 to xk. Okay? So this is how it looks like. Okay? The time, again, it is implicit, and it doesn't have to be time. So a few examples. I'm not going to spend a lot of details on this, right? But just to get a sense of how you can write simple problems. So this is a tracking example. So you know, if you're tracking the path of a missile, and k1, xk2 is the x and y location, let's say, at time k. vk1, vk2, the x and y velocity components at time k. So you can write an equation of motion, if you like, and this is what is called the constant velocity model that looks basically like this equation. Okay? So xk is a times xk minus 1 plus some noise that is given by that. And since the first component is displacement, location, the second one is velocity, you can see that this is sort of a time integration equation, right? You can see, for example, that the location, the x coordinate at time k, it is really the x coordinate at time, bless you, k minus 1 plus t times the corresponding velocity, okay, plus some noise. So anyways, this is, again, the details are not important. This is a tracking example. in this case, basically a linear problem because, A is a matrix that I'm taking it to be constant. And here is the transition law, okay? So the probability of xk given xk minus 1 is axk minus 1 is a Gaussian with mean axk minus 1 and a covariance, basically a variance matrix that is defined by the noise sigma. I can bypass this, right? It's a very interesting example. I know some of you want to make money, and I did not put this just by accident, but if you're interested on prediction of where the stocks are going in the market, right, this is a huge subject in econometrics, and if you're really interested, some of the best reference books on sequential Monte Carlo methods are in econometrics. And some examples are so standard, if you work in this area, you have no choice but to actually compare this with standard tests like the volatility test that we will see later on in these lectures. So this models basically in discretized form look like that, and where the noise basically comes from a Brownian motion plus a jump process. So once a while, at arbitrary times, basically xt jumps, okay, so you want both sets of noise. And so when you integrate this equation, this ODE, you get something like that, and you can easily put it on the form of a Markov model. So let's enhance this. Before we had a single state x, and if you remember, I call the joint distribution of the x's, I call them the prior model. So now what we're going to do is we're going to assume at each time that we have some observations y. I should have marked this, to indicate that they're observations. But basically now you can appreciate why this is the prior model. So we're going to start with all the states being unknown, and then we're going to try to estimate them given the y's. All right? So we're going to need to write down some likelihood model for the observations y. And together with the prior model, we are going to estimate some posterior of the x's, and then we are going to figure out how to compute the posterior. And we will first discuss some cases where there are analytical solutions, but really of relevance to the lecture today are problems where there is no analytical solutions, and all of these states have to be estimated numerically. Now, what I want you to appreciate before I write down the likelihood and the posterior is if you keep doing this forever, right, it is computationally a very intensive problem, and you want it sort of to be able to say something about the posterior of the axis without having to worry how big n is. Because if n goes to infinity, you don't want to be in trouble and have an explosion basically of type of calculations. You need, can you do sort of an inference of all of the states x's, but at the cost of sort of one increment of type of calculations? And it's not a trivial problem on how that will be possible. So let's figure out the likelihood. So you remember again, this is the probability of the initial state, this is the transition probabilities of x, and this is our likelihood model at each step. I want you to carefully remember the notation here, f, for the evolution of x. The likelihood model is g, and the assumption here is that yn depends only on xn. I'm going to try to cover the lecture today without mentioning this is independent of that, conditional on the state, etc., because these are sort of topics we're going to cover next semester, okay? So I'm going to sort of have to force you to read proofs that we will be able to cover sort of visually, more or less, in the course next semester. But right now, I want you to consider that yn only depends on xn and is given by this function g. So the data given the states are IID, so I can write the likelihood as the product, if I have n data points, as the product of these functions g of y given xi. Clear? So again, initial state, transition probability. Basically, this is a Markovian model. Xn depends only on Xn minus 1. This is my likelihood model. Yn depends only on Xn. So, if you see later on that I also have here condition on lots of previous x's, they don't matter. Xn contains all the information I need to know to compute Yn. Okay? All right. So, some examples. This is a linear Gaussian state space model. So you start with x1 from a Gaussian. The transitions basically are defined by this linear equation. Xn is some matrix times Xn minus 1 plus some noise. The observations depend only on Xn. So obviously you can put this is directly what we had before, okay? And it's a linear system. If these matrices A, B, C, D are constant in time, I'm not going to do all the derivations today. I'm going to highlight it, but basically we can get this problem in closed form analytically, okay? That would be your basic Kalman filter equations. I mentioned about finance engineering and econometrics, a very famous problem that if you develop any algorithm, if anybody does any project in this area, we have to test your programs with the so-called stochastic volatility model, and there are many of those. And it looks simple. You start from x1, sample from this Gaussian. Xn is some constant times Xn minus 1. But look where the complexity comes. The complexity comes, you don't have this likelihood. It is nonlinear in Xn, in the state. Okay? And you notice the noise is not additive, right? Wn is basically multiplicative. It comes in the form it comes here. So the likelihood model looks as a Gaussian and has a zero mean, all right, because this has zero mean there, and the variance is beta square exponential of Xn. So the fact that you have this exponential there makes this an interesting problem for testing algorithms. Let me just look at the problem on the bottom, because I think some of the I'm going to show you results on this on the lecture on Wednesday. For those who are working on tracking problems, this bearings only tracking has a very simple form. Okay, so yk, the observation is the inverse tangent of xk2 divided by xk1. So can you guess what you're actually measuring here? Obviously, you're tracking the path of an object. What are you tracking if the observation looks like that? Exactly. A what? Huh? Yeah, but what is it? So the tangent of yk, it says equal xk over xk, x2 over x1. So what are you measuring? Exactly. So you're measuring an angle. And why, again, this is an interesting problem. It's very practical, of course, with lots of generalizations, but you can look at the likelihood model. It's basically a highly nonlinear function of the state. So it's not your sort of trivial problem where everything is linear. This is inverse tangent as a mean of x2 divided by x1. So that makes it an interesting problem to test things. So if anybody, I have to admit, sort of very disappointed that nobody picked up sort of any of the interesting dynamical problems to do for project. I thought some guys from systems in EE will work on some aspects of sequential Monte Carlo, for high dimensional tracking, but that didn't happen. Everybody wants to do deep things, you remember? Very deep. Okay. So the state space model, so this is what we want to compute basically. This is our objective. The objective is to compute the probability of x from 1 to n. So when you see this notation, that involves x1, x2, up to xn, given the observations y1, y2, yn for all n, right? So basically when we start, at step 1, we need to compute P of x1 given y1. At step 2, we want the join of x12 given y1, and y2, and at step n we need this, and we need to do this sort of in a way that the cost will not explode with n. I mean, this is basically the important thing here. So obviously this is the posterior of a model with this prior that we wrote before, and the likelihood looks like IID data, and the likelihood for each data point is given by this function g. So let me talk a little bit about things you may have seen. Do we have a class actually on these topics in EE or somewhere? On does anybody teaches Kalman filtering and all of these things? Maybe controls or something? I'm curious. Huh? You took a class? Here? No. Okay, then we're not interested. All right. Huh? It's not regular. Okay. I do hope, as we hire more people, right, on this whole area, this is sort of a very fundamental course that you need to spend a semester, because it has implications everywhere, and it's not just, Kalman filtering, right? There is much more to it, and so it's essential to have a course devoted to this subject area. I mean, there's a whole community now that they rediscover these things and they dress it up with nice mathematics, and they call it data simulation techniques, but it's really rediscovering things that are already known in the literature for many years. So you can do lots of fancy applications using this type of things. All right, so this is the prior, this is the likelihood, and so we write the posterior basically as the join of x and y. I cannot keep saying all the indices, but again, the notation, when you see bold with subscript n to 1 means x1 to xn, okay? There are two dots there, okay? So what is important here is that this joint is really the anormalized version of the posterior of x given y. So if I just multiply the prior times the likelihood, right, that's the anormalized posterior. And you remember when we do sampling, we're really interested to be able to sample directly from this, but really only having available this anormalized posterior. I mean, we will see that we can compute this easily, but generally, right, this can be a very difficult thing to do for nonlinear systems. So the anormalized posterior, easy to remember, right? Because the Markovian model is the probability of the initial state times the product of all the transitions for the states times the likelihood term, okay? And this is the denominator. If you're interested for the marginal, this is how the marginal is basically the normalization factor. So notation, we're going to indicate the anormalized part of our target distribution as gamma, all right? So the gamma is basically the joint distribution of x and y from 1 to n, okay? And Zn is the normalization factor. Now you say, why, we're really interested on this, I mean, to keep track of, it's like if you already have calculated, the posterior of x1 given y1, why you don't just pose the question, give me x2 given, let's say, y2? Well, this probability, this posterior contains much more information than any marginal you can imagine, okay? And as a matter of fact, we will see that this concept of filtering and smoothing come to play a role here. So really, even if you care only about point estimates, we're really interested to compute the whole posterior of all the states x1 to n given the data y1 to n for every n, all right? Not for a particular n, but for every n. So if you have that, somebody, maybe you can calculate the most probable states x1 to xn. You can find map estimates for any of these components, all right? So if you integrate everything out except the component k, you have a posterior for xk, and then, you can find the map estimate, or you can compute a posterior mean. This goes back to the same way when we're discussing about posterior distributions, right? The posterior, it's the main Bayesian ingredient, so if you have that, you can play with point estimates and do maths or anything you want to. So let me do an example that one of my colleagues used to show it as a showcase, basically, of where the normalization factor of this distribution has lots of practical meaning and where it's going to be useful. And so let me see, is this the example? What slide we are? 24, because I need to start jumping now. All right, so this looks good. So let me put all of this up and define the problem. We have our Markovian state again, all right? And I define a time n. It says the probability for a particle to be killed is given by 1 minus g of xn. Okay? So the word kill can mean different things. Can mean failure of a component in a dynamical system. The plane flies, right? And you say, what's the probability at a given time the engine will fail? So I define here that the probability for the particle here, it's particle moving in a random medium, it's defined by this, but it's again up to interpretation. This probability of failure is given 1 minus g of xn. Okay? And the problem, it says the following: compute the probability for the failure to take place after time n. So again, let me rephrase the problem. Our transition of states as before. The probability of failure is 1 minus g of xn. So at every, when you are at state n, the probability to fail is 1 minus g of xn. And we're asking to compute the probability that the time of failure is higher than n. Very practical problem, right? I mean, if you're a mechanical engineer, civil, electrical, I can think of 1,000 cases where you basically have to do this. So can you give me, I don't have lots of time to go through all the slides, can you tell me how the answer will look like? What needs to happen for the probability of the failure time to be greater than n? Just use simple logic here and let's figure out what the final result will look like. To fail at time greater than n, what does it mean it has to happen up to time n? One person at a time. So what has to happen, aloud, and I will repeat what you say. So let me ask the following thing, all right, so I can understand what you said. For the failure to happen after time n, what needs to happen at time 1? No fail. But to not fail means you need to be born first. Right? You need to be around because, how can you fail if you don't exist? All right? Then what does it mean at time 2 not to be at time n? What does it mean at time 2? You need to transition from state 1 to whatever state in time 2, and then what do you need to happen? What needs to happen at state 2? Not to fail. All right. So let me see somewhere there is a result. Come on, I need the final result. Does it make sense that the probability for t to be greater than n is given by this integral? Just look at that and just tell me if that makes a little bit sense. I mean, you can read more in the notes, but the only thing from everything we discussed that obviously we did not mention is this term here, because when you tell me you have to be at state 1 and not to fail, you didn't tell me what I need to be at state 1, so I can be anything. Right? So there's an integral there with respect to state 1. Similarly, when you go to state 2, it's it can be anywhere, and that's another integral over x2. So basically, so what is this integral from mathematical point of view, based on our notation before? What is this integral? Yeah, but we had, you remember we defined the unnormalized posterior as gamma, and then on the denominator we had something as z, a normalization factor. What is this really? Huh? You have your computer in front, what does it say? Help me. So what does it say? What is it? It's the normalization factor of time n. So you can immediately see that this concept of, saying something about this probability of failure really requires the normalization factor, all right? And up to now, you remember in everything we did, we used the normalization factor for, model selection and model comparison. Well, you know what? Here's the normalization factor to say something about the probability of failure in this dynamical system. So a lot of utilizations, and obviously you need to do this calculation carefully, and that's something we will try to discuss today. Okay. All right, so we don't need any of this. So let me see, what does it say there? It says Bayesian recursion formulas for the state space model. So what I need to do, again, this is very elementary topic, but lots of you maybe have not seen it. I want to tell you about the analytical, basically, recursion formulas that someone can write down, okay? The spirit, of course, is that even if we can write down things analytically, for a real problem, these analytic expressions will not be very useful, right? So we're going to try to address this numerically, but certainly if there is an analytical solution, you need to know it, otherwise you can perceive that this class doesn't teach you anything of substance. So we want to calculate this posterior of x1 to n given y1 to n, okay? I am going to try to do the fundamental derivations, without using any language that of conditional independence and the like, okay? So please pay attention to what I'm going to do, because the derivations are very simple. You see lots of equations, but they're really very simple. This is what we want, right? At any n, we want the posterior of the x states given y. Can I write this probability as this red numerator that you see there? We agree that's correct? Bayes rule? Yes? Is this equal to the red numerator? Yes? Okay. Is the blue equations basically cancel each other? Is that okay as well? Look at it carefully. There's nothing there. I just added the blue on the numerator and denominator, obviously for a purpose. Okay? So let me rearrange. I'm going to have this divided by that. Now you can maybe appreciate why I did this trick, because effectively this would be the join at time n, this could be the join at time n minus 1, and the whole idea is to do this in some incremental fashion. So I put this in the this term in the numerator, this in the denominator, times that. Okay? Now, look at the first fraction here. All right? And remember how the joint probability distribution at time n and n minus 1 look like. And can you see why this ratio is exactly this product of g and f? The first, this fraction there, can you see why it is the product of g times f? You remember how we built the joint probability distribution is the probability of the transition probability is f of xn given xn minus 1, and then the likelihood modulus of yn given xn. So really the difference of those two terms is this times that. Yes? All right. So nothing new. Do you agree with me that using Bayes' rule, basically this is equal to that? have to get accustomed to this notation, right? We have dynamic problems. You know, this y from 1 to n, you know how you can write it? Y from 1 to n minus 1, comma, y, n. Can you see Bayes' rule there? All right. And of course, I keep this as this, all right? Because obviously this term here is like this posterior by the time n minus 1. So basically, if you rearrange, you can write this posterior time n of all the states given all the data up to time n as this likelihood model times the transition from n minus 1 to n times the posterior at n minus 1 divided by this, I have to admit, weird looking term, okay, which looks like a very difficult term, which is the probability of yn given the previous data. There is no states involved in this denominator. So this term came from this fraction, the second term, all right? So it looks a little bit weird. But right now, this looks what the calculation gives. So let's calculate the probability of yn given y from 1 to n minus 1. Here's the trick, which is sort of universal trick in doing these calculations. Can I write this probability as the marginalization of this? The only thing I have done is I plug in an xn and I integrate it. Yes? All right. Is this equal to that? And what has taken there? And you know, you may accuse me that I'm going too fast and some details are hidden, but here's some common sense. Tell me, what have I done to go from here to there? What have I done to go from here to there? Basically, there's one step only, and one assumption that is common sense, and you can show it with, it's maybe shown in the next slide, but what do I need to do to go from this to that? I mean, I can see here it says yn, comma xn given that. So can I write this as yn given this term and that term times the probability of xn given yn 1 to n minus 1? So what has happened here? I omitted this term here. When I write this yn given xn and all of this, what happened to y1 to n minus 1? I don't need it because yn, my likelihood depends only on xn, right? So I throw it out, okay? All right, so, there are, you know, you may ask me then, and how do I compute this term? This term looks very complicated, right? So what I do another trick. So I am adding an xn minus 1 there, and then I'm integrating xn minus 1 in addition to xn. So here the integration is an xn minus 1 and xn, okay? And can you see now what am I doing again with Bayes' rule of the second term? So I'm writing here Bayes' rule, the probability of xn given xn minus 1. What has happened to this term? Is not needed. Why? Because the state xn minus 1 defines uniquely xn, right? It's a Markov model, times the probability of xn minus 1 given yn n 1 to n minus 1, okay? So here is the final answers. If you want to compute the posterior effects of all the states up to n, given all the data up to n, what you need to do is you need the following. You need a likelihood model, which is not a big deal. You need the predictions of all the states, including xn ahead of the data n minus 1. So this is really a prediction step. And where is that prediction? All right, that prediction is basically this product there that you see. All right, so that product allows you to compute this term, okay? And then you have in the denominator this. What is that? The denominator is this nice product of the likelihood, this transition probability, and this term which, since we're going to do things incrementally, we know it from time n minus 1. So just, again, look at the bottom two equations, right? Prediction and update, and convince yourself that if you start from time n, this will work if it is correct. All right? If it is correct, will you be able to actually do prediction at each time? Will you be able to predict one time step ahead of your data? Will you be able to do this calculation? Will you be able to find this times that? At each time, will you be able to do this calculation? Yes, you know this. Do you know this? From where do you supposed to know this second term? Well, from the previous time step, because we're supposed to do this incrementally. All right? So if we know this, then you know this term in the numerator, you know this likelihood term, and then you need this P of yn given y1 n minus 1. So this is the probability of seeing yn given all the other data. And what is that? Is this integral. And what is the only thing you need here to calculate this? Is basically the posterior of the state xn minus 1, given all the data up to n minus 1. Now, we don't really know this. We said, iteratively we know this probability. I'm sorry, what was it? Iteratively we know this posterior. How do you get this if you know that? From this, how do you get this? Everything else has been integrated out, right? And you only keep that particular term, and that's it. Okay? All right, so that's why it's important that you keep this posterior of all the states every time. Okay, so these are the recursion equations, and these are what is called the forward calculations, forward filtering equations. So this is a filtering distribution. This is the corresponding predictions ahead of the data, okay? And I'm not going to, basically we discussed everything. You can actually, the only thing you're interested are the marginals. I give you the updates of these equations, the form of these equations, where the only thing of interest is the state xn. So if you don't really care about the previous stages, you keep moving forward, and the only thing you want to care is about xn, all right? You can do this. It's much more efficient than this sort of calculation, so this is very general. If you want only the state xn, these updates are very useful, okay? You're going to find all of these equations in lots of books, right? So this is more or less what is standard, okay? If you only care about xn, simple sort of, Bayes rule type of calculations. This is how the updates will look like, where the only thing you need to keep track is xn given your observations y up to time n. Okay. All right. So one of the things I'm going to have to tell you, because we already discussed that this, for example, it comes up when you refer to failure probabilities, is to calculate the marginal, the likelihood, basically, the marginal likelihood of your data, right? And the marginal likelihood of the data, somebody may say, you know what, if I have the joint probability of x and y at each state n, I can go out and integrate x, all right? That would be extremely expensive calculation to do, right? So, again, we were talking about the posterior, but it was really an unnormalized posterior, so it was really the joint distribution of x and y. So somebody will say, to calculate this, integrate all the x's out. Well, this formula actually, it's much more efficient because it tells you to calculate this marginal likelihood, you only need to compute this probability of the data ahead given data up to k minus 1, and we derive this. All right, we gave a nice expression of this, and you notice the integration that is required to find these terms is integration in two variables, not all the variables. Can you see that? I mean, I can compute this by integrating all the x's from 1 to n, or I can do this calculation where I have to compute these conditionals, and each of these conditions require integration in two states only. So computation is very efficient. All right. Now, this, so it was what we call the forward filtering problem, but there is another problem which is of interest. Let's suppose that you run this type of Markov chains up to time n. So let's call time n is your final time, okay? You run a dynamical system up to time n. And if somebody tells you, I am going to give you all the data you collected up to time n, can you tell me what's the probability of state xk? This is what is called the marginal smoothing distribution, right? And it's smoothing because now you don't use data only up to time k, the way we did before, but you use all the data up to time n. You see that? So this is sort of an offline calculation. It's not something you're going to do incrementally in time, but once you complete all the data, you can go back and actually improve the information you have about state xk, because you account not only for observations at time k in earlier times, but also you account for future observations. In my early days, when I was a PhD student and I was working on inverse problems, I don't know, don't ask me, in life, you get what you get from education. And so I was working on this future information method to regularize some problems in fluid mechanics and heat transfer. Nobody actually would point me to the fact that this is such a nice, well-established area in state space models, because I had no idea what's a state space model. All right? So now I have to penalize you. You have to know these things, because there are no excuses to say I never heard of state space models and these filtering techniques. So the idea here is introducing future information. It regularizes the values you get for xk, so they're smoother now, all right? Because future tells you something about the present as well, okay? So the calculation actually, I'm not going to prove it because it follows similar things with the forward calculations, but it requires two things. It requires that you do a forward calculation similar to what we discussed in the previous algorithm. So you need to compute first. So you go forward from time 1 to time n. You compute this marginal at each time k, given the data up to time k. But also you do a prediction one time ahead, given the data up to time k. And we gave equations on that. All right? So you compute this all the way up to time n, and you store this information. And then there is a backward calculation where you have to believe me with simple application of Bayes' rule. It gives us this equation. And it says the probability of xk given all the observations up to time n is given by what you see here. So let's see, can we compute this? And what do we need to do to compute this integral? Look at all the terms and tell me if we have everything we need to compute the integral. You don't have a problem with f of xk plus 1 given xk, do you? Right? That's the transition probability, no big deal. Do we know p of xk given y1 to k? That's the filtering probability from the forward calculation that we did before. Nice. What's the denominator p of xk plus 1 y to 1 over k? You remember that's the predict step in the previous algorithm, is predict one state ahead given the data to time k. All right? And what is this? This is what we want to compute, and compare this with this term. This is what we want to compute, and now it requires this. And see now why we call this a backward calculation. The only way that this calculation that you see here will work is if you do this calculation what? Starting where? Starting at the end and going all the way in the beginning. Okay? So basically, to compute this smoothing probabilities, you have to run a forward calculation, save all these values, and then you do a backward calculation starting on time n, and use this update, and then go basically all the way to the first step. Again, next semester we will see this for very general models, not just dynamic models, where all of these things will be sort of simple message passing in a graph, right, in a generalized way, where this equation sort of can be derived in seconds without much pain or using Bayes' rule all the time. Okay, so we did the forward, we did the backward, so these are sort of standard historical calculations. I'm only going to spend 2 minutes on this because we are not going to elaborate very much. These models, they have parameters usually. So when you define, for example, the transition probability from xn minus 1 to xn, there are some unknown parameters, right? Because you don't know the dynamics of the problem. I mean, you can appreciate, right? Maybe, there is, the dynamics, there is something in the expression of this model that you don't know the details. It's not like xn given xn minus 1 is like 3 times xn minus 1. You don't know that. Right? You don't know what the underlying dynamics is because this is a noisy system that is not under your control. So these parameters, let's call them theta. And similarly, maybe you have a different set of parameters, but I indicate all of them under this letter theta. The observation law also has its own parameters. I mean, the most trivial case would be if the noise in these models is theta. We don't know what the noise is, the variance in the noise, so that's unknown. All right, so you're going to have to compute this noise. Now, the way we treat parameters in this state space models is quite easy actually, but you have to be careful when you program it. So the states xn are unknown, theta is unknown. We call this dynamic unknowns, right, because they change with time, and we call theta static unknowns because they don't change with time. So here's the trick. I am going to define a new set of variables. Rather than having the state x, I'm going to define z that consists of x and theta. And I'm going to write down a new transition model that looks, and a new likelihood model that looks like that. And in particular, I want you to concentrate on this transition model and tell me if you're happy with it. Just a trick to basically use the same equations as the ones we wrote before. Can I write this transition from Zn minus 1 to Zn as such? What does that say? What is this? Is the probability of transitioning for of my states from xn minus 1 to xn, which is, depends on theta. And what is the first term? What does it say with words? That theta is what variable? Is static, is constant. Okay? So if you do this trick right, somehow all the machinery of these state space models fits nicely. I'm not suggesting necessarily that this will be an efficient way of doing it, but mathematically at least, right? You can use the equations we wrote before for this problem where there are parameters. In the notes I discuss various ways for computing the static parameters. I'm only going to mention this for those who have taken previous course in machine learning. The expectation maximization algorithm is a key ingredient for doing these calculations. And effectively, the only thing that you need to be able to do is taking averages with respect to this posterior of the states where the parameters have been set in the previous sort of you update the parameters, and I is an index of iteration. So if you can calculate this integral, then you can maximize basically this joint log likelihood, right? And this leads to the EM algorithm. But the way I have written it in the notes, I have used this identity, which is called the Fisher identity, which is exact, all right? And if you approximate this, you get this EM algorithm. We will certainly spend one lecture on the EM algorithm. I'm just telling you, come back to this slide when that topic is covered later on in the course. Okay. So all these equations that we mentioned, if the system, all the equations, if the function f is Gaussian, if g is a Gaussian, then you get the Kalman filter equations, and there are analytical update equations that fit in what we had before. So you can appreciate, if I can go back to these equations, right? You can appreciate that if all of these distributions f and g are Gaussian, obviously when you do all of these updates, product of Gaussians are Gaussians, marginalization of Gaussians is Gaussian, so everything comes to be Gaussian. So the Kalman filter, what it does is it writes these equations in a beautiful, nice form, which we're not going to do because we have no time. And if it happens that your system is really non-linear and things don't fit with the Gaussian paradigm, you can do a linearization of your equations and use what's called extended or unscented Kalman filters, which are actually sort of trivial approximations of these update equations that I gave you before. So assume that you know everything about Kalman filter because it only utilizes the update equations I gave you before and plugs in the approximations for f and g to be Gaussians. All right, so let's talk about, reminding you about importance sampling and see if we can do anything with importance sampling in the context of our difficult dynamical system. All right, I have a lot of reviews, so I'm going to try to go fast on these reviews. So I remind you the Monte Carlo approximation of a distribution. So if we want to sample from P of x, we take n samples. So this is the empirical measure that we used, in this Monte Carlo approximations. And if you plug in this in expectations, you get your Monte Carlo estimator 1 over n summation of effect fxi, and the notation, basically the samples are from the actual pi. So the whole idea of sampling methods is that this pi is difficult to sample in general. So yes, this looks very nice, but it's not going to help us. But these Monte Carlo simulations are essential because basically this is what we use for all the other methodologies. So I remind you with the Monte Carlo estimator of the expectation that this is an unbiased estimator, and the variance is the variance of f basically divided by n. So don't forget those results, okay? So unbiased, so if you take the expectation of this, you get the exact expectation of f, and the variance is the variance of f divided by n, or if you want, using the central limit theorem, something that looks like that. So we go back to our notation. We are going to assume that pi is not given. We have an normalized version of pi, and this is the normalization coefficient. And I remind you, important sampling is to sample from a distribution Q of x, all right, and define weights that they are gamma divided by Q. And we have shown that pi of x is w times q divided by this integral. Actually, because I know you forgot about it, plug in this inside this and convince yourself that it's correct, right? Put it for w gamma over q. What do you get on the numerator? You get gamma. And what do you get on the denominator? You get the integral of gamma, which is the normalization factor. Okay? So the idea is we're going to take samples from Q rather than from P. And again, we're going to have this major constraint we discussed several times, that in the regions where pi of x is positive, q of x has to be positive. But now we're going to weight the samples with this w because we don't really sample from p, we sample from q. So this is the idea of importance sampling. And so the samples we take for q lead basically to a Monte Carlo approximation of q exactly as before. All right, these delta functions concentrated at x. But where is it? The sample for the distribution for pi, this is a reminder, all right? The distribution for pi, yes, has delta functions here, but then has these normalized weights wi. This is capital W. And what's the definition of capital W? Is little w at xi divided by the summation of all the weights. You remember that? When we did importance sampling? Does it click? All right, so this is the whole idea, right? That the samples come from the distribution Q. That's why Q looks like that. All right, but when you plug them in pi, which was looking, do you remember WQ times, divided by this normalization factor, basically the distribution, the approximation looks these delta functions, but now you can see there is this normalized weights, which are the weight divided by the sum of all the weights. Okay? So now, and with this, let me see if, and with this actually, because this is going to be important, we show that the approximation to the normalization factor of the distribution pi is 1 over n times the summation of all the weights. It's very important. So when you do this important sampling, right, and you need the normalization constant, basically the only thing you have to do is sum the weights, okay? We prove this in the important sampling lecture, okay? All right, so the normalization factor is nice. Now, can you remind me when we plug in this in the expectation of a function f of x with respect to this important sampling approximation, is the approximation comes to be biased, unbiased? What did we conclude in passing? I did not give you the detailed derivations that were in the notes, but we said something. Obviously, it's going to have some variance, right? But is this the fact that we had a ratio really of two estimators? What does it make the approximation using this pi? It makes it biased, right? But the bias, it's bias squared goes like 1 over n squared, so it's not very big, but it's not an unbiased estimator. And so the bias basically is given by this term. If you write papers on this, you better have these results, right? So don't go and say this is an unbiased estimator. This is the bias of important sampling estimators, and the variance basically it's 1 over n times basically the variance of, as you see here, is w times f minus the expectation of f squared. Okay, actually they are very nice looking formulas. Okay, and but unfortunately you get this extra term, which if n is large, this bias term is not very significant. Okay. Let me ask the following: is the estimator of z biased or unbiased? Just look at the, for the estimator of the expectation, we were coming up with the ratio of two Monte Carlo estimators. Looking at this, the way we compute it, you think this is biased? What do you think? So when you compute the normalization constant, I don't see any ratio of estimators, right? This was just a weight, all right? Q is there, so this is one Monte Carlo estimator, so obviously it's unbiased, okay? So obviously the expectation of this estimator is the exact z, and the variance 1 over n times the variance of gamma over divided by q. So this is sort of an interesting result that the normalization constant you can come with an unbiased estimate of that. Okay, let me see what I can tell you now. So I'm actually going to jump all of this. So we go back to our real problem. This is the posterior of n states given the data up to n, and the anormalized posterior is the numerator. That's our gamma, and it looks like that. So the Monte Carlo, if you do, just Monte Carlo sampling of this at time n, will you agree with me the Monte Carlo approximation of Pn of the posterior will look like this? The notation is very important. So how many samples do I have here at each time? I mean at time n? So when you do this Monte Carlo estimate, right, and you say, you have all these delta functions, each of these delta functions is in what space? How many variables? N, all right? So remember, I goes from 1 to n, but for each I have states from 1 to n. So we have to sample from x1, x2 up to xn, all right? So every time we take samples up to n, but apart from that, the notation, it's exactly the same thing as standard Monte Carlo. So again, if you can do this is gives you an unbiased estimator of expectations with respect to this posterior. We know what the variance is, the standard Monte Carlo results. But obviously the idea here is, this is, we work under the assumption, and I gave you examples today, where this is very complicated distribution. You cannot really sample directly from this. Certainly you cannot sample from this when n goes to 500,000. All right, cannot do this. All right, so we cannot do this, then what can we do? All right, so let me see what we can do, considering our time limitations. So the idea is, we cannot sample from this posterior, so we're going to come up with an important sampling distribution, which I denote as Q of x 1 to n. And be careful here with the notation. When I say given y 1 to n, what does this notation mean, right? When I have an important sampling distribution, it just simply means that if I want, I have available information of the data from 1 to n, but really it's a distribution of x1 to n. In other words, I can completely just get rid of this. It's not conditioned on anything. When I write this equation, it tells me, and if you want to use, in coming up with an approximation, if you want to use the data is available to you. All right, so it's not, you can interpret the condition, etc., but I want to basically emphasize that there's a subtle difference basically from this posterior distribution. So will you agree with me that the important sampling approximation, now I can write this as the weights times Q divided by the normalization factor? Can I do that? It's a copycat of the previous equation. The only thing is, instead of having one state, I have x1 to n. You remember before we had this posterior given w times q divided by the integral, and now the integral is an integral over the n variables. Yes? All right. So, if the previous calculations, you cut and paste them, and literally this is what I have done, right? I can write this posterior here, the Monte Carlo approximation of the posterior, as this delta function summation, where I have capital N samples, and each sample is x1 to xn, with weights that corresponds to little w's divided by the summation of all the w's. Haven't really done anything. It's the same equation I applied to our dynamic problem. The same equation applied to our dynamic problem, and the notation looks messy, but really there's nothing there, all right? It's, instead of having 1x, I have the sequence of x1 to xn, right? Because my posterior is basically this posterior here. Okay, so this is the Monte Carlo approximation. So So the weights, basically, these are the normalized weights, all right? Obviously, this is not desirable again, because you can see from here, it's like, how can you go and take samples? Can you imagine, capital N being 500,000, and every sample will be 500,000 dimensional? I mean, how can you do this? So the idea here is, can I actually use the samples that I collected at n minus 1 and only sample at a sample at time n? Would that be nice? Right, so every time you only sample, in sort of at that time, and you keep everything else, whatever it is. All right? So why should I go and sample again all of these things from 1 to n? So let's see if time will allow us to do that. All right? I'm going to come back to these equations, all right? But let's try to give you something concrete so you can sleep with. All right? So here's the idea. We sample x1 from this normalized posterior at time 1, all right? Okay. And this is my, my important sampling approximation in time 1. Look at it, it's the previous equations written only at time 1, okay? So I only sample x1 from Q1 of x1, okay? All right? And my weights look as gamma 1 divided by Q1 of x1. Now what I need to do is I need to go to time 2, and obviously I need to sample x1 and x2 from an important sampling distribution that looks like this. I will restrict myself here so we can make life easy. How about if the important sampling distribution has the form that you see on that yellow line? Let's try to appreciate it. It says, if you want to sample x2 now, once you have sampled x1, given y1, you sample only x2, given x1 from this proposed distribution that you see on the second term. Can you see that? It says to sample x1 and x2, sample first x1 at time 1, and once you have x1, then go and sample only x2. All right? So in the previous slide, I mentioned we already have sample x1 from this. How about now if I take this as my important sampling distribution and sample x2 according to this rule, which is given like that? All right? What happens? This is how the weights will look at time 2. All right? And I'm starting, by the way, with a fundamental definition. This is my normalized posterior at time 2 divided by my important sampling distribution that I said I'm going to put it in this form. Then I multiply by this term, divide by that. What is this? What is the first fraction there? It's the weight W1, and then what is this? This is basically my incremental weight when I go from time 1 to time 2. Okay? So here's the idea. You sample x1 from Q1, you compute this weight W1, and then to sample x2, right, you're going to sample it from this distribution, okay? And then your new weights will be basically the old weights times this incremental weights. So every time you only sample at that time, you keep the previous weights, you keep only the previous sample, and then you update. And the algorithm basically, if you use this trick at all times, all right, let me just give you the general expression for the weights. The weights at time n will be the weights at time n minus 1 times this incremental weights. Now, if you look at this expression, I'm going to leave you there. It looks sort of a little bit concerning because you notice the Qn seems, to depend in general on all the previous samples. So we're going to write this. I already did a thing on the previous slide. but we need to be sure that this increment only depends on xn minus 1, not on all the x's. Right? You don't want to keep track, when you're on 500 times step, to keep track of all the samples you took up to 499,000, whatever. You want only to keep track of the previous xn minus 1, right? And of course the previous weights. And you can do this. I'm going to just, it's 4:46. I'm going to give you let me see if there is a final update of this. Okay, I'm going to leave you with this equation on the bottom. Okay? The weights at time n, the weights at time n minus 1, times basically a proposal distribution at time n that only depends on the state at n minus 1 and the measurement at time n, and f and g, of course, at time n are our normal transition state and likelihood model. So the idea, get samples up to time n minus 1, compute this weight, update the weights, and sample from this proposal distribution at time n. So the cost as you go does not grow exponentially with time. It's basically like repeating the same calculation with the same cost at each time.